Hi everyone. My name's Geraint Palmer. So I am a mathematician and lecturer at Cardiff University, so I'm local here. And my field of research is called operational research. And operational research is using maths to solve managerial problems. In general, we do things like modeling, which is describing things using mathematical language, and optimizing things, finding the best of something. And today I'm going to talk about a project I did where I implemented this all in Python, but I'm just mainly going to talk about the mathematics today, called multi-objective linear programming to find the best Pokémon team. So this work was originally conducted and published in Welsh. I published in a Welsh language journal called Gwerddon. And Gwerddon is a journal that's funded by the Coleg Cymraeg Cenedlaethol, which the aim of the journal is to make sure that academics like myself have the opportunity to conduct and publish research through the medium of Welsh, and also that there's enough quality academic literature in Welsh for other academics and students to read. To Pokémon then. So Pokémon is a franchise of Nintendo games, and it came out about 27 years ago now, so this is not really a cool modern talk. Okay? But if you don't know about it, the first games looked like this. So the aim of the game, you go around this virtual world, you collect little creatures called Pokémon, you build a team of 6 Pokémon, and you go around battling other teams of Pokémon. And a Pokémon battle looks like this, where you send your Pokémon out one at a time. There's a few attacks you can choose from. You hurl attacks back and forth at each other, your health bar goes down, and then you lose. Or sometimes win. So one of the big things you do in this game is trying to find the best team. Like you try and construct a team of 6 Pokemon, you try and give each Pokemon moves, and you try and work out which is the best team, which is the most versatile that can work in different battle situations. So this study then is going to focus on the games Pokémon Sword and Pokémon Shield. These were the games that came out in 2019. And in those games, there is a roster of 739 different Pokémon species or variations. So we can consider them unique species of Pokémon. Okay? And you're trying to build a team of 6 of those Pokémon. Each of those Pokémon can learn 4 moves, and in the game there are 841 different moves coded into the game. And each species of Pokémon can learn a subset of those moves. On average, that's around about 68 moves per species of Pokémon. So there's lots and lots of combinations of teams and configurations that you can come up with. Okay, so a little back of the envelope calculation tells me there's about 1.8 times 10 to the 20 different configurations or teams that you can create in this game. Okay, so if you've created a team in this game, you've probably created a unique team, which is quite cool. To put that into context, that is somewhere between the number of grains of sand on Earth and the number of stars in the observable universe. So we can't really just take all these configurations, sort them, and find the best. We need something a bit cleverer than that. Okay? So I'm going to introduce you now to a mathematical technique that I thought at the time would be able to do something a bit cleverer than that. So this technique is called linear programming. It's not a big secret. It's a very common technique. But I'm going to introduce you this through an example. So this is the example I always use. So let's say I am a paint creator, a paint manufacturer, okay? And I can make £50 a profit on a gallon of paint A and £60 a profit of a gallon of paint B. To create these paints, there's 2 ingredients, X and Y. To create a gallon of paint A, I need 4 pints of X and 5 pints of Y. To create a gallon of paint B, I need 6 pints of X and 4 pints of Y. But I'm constrained every day. I know I can only buy 24 pints of X and 20 pints of Y. So I need to know how much of each type of paint, A and B, should I produce every day to maximize my profit? Okay, so that's the situation. I can model this mathematically, so I can describe this using mathematical language, which is this. So I'm going to let the symbol A represent the amount of paint A I am producing in gallons. I'm going to let the symbol B represent the amount of paint B I am producing in gallons. And therefore, I can now write down what my profit would be in pounds. My profit would be 50A plus 60B. And I want to be able to maximize that. Now, my constraint, I am constrained by the amount of X and Y that I have. So how much X would I be using? So I would be using 4A plus 6B of X. So I need 4 pints of X for A and 6 pints of X for B. So I'd be using 4A plus 6B of X, and I need to make sure I'm not using more than 24 pints of that in a day. Similarly for Y, then 5A plus 4B must be less than 20. Okay? So that is my mathematical model of what's going on here. I now need to go solve that. I need to go find the A and B that makes that true, that maximizes this. I can do that by considering what I'm calling a solution space. So this solution space is a Cartesian plane where I've labeled one axis A, the variable A, one axis the variable B. And every point on this plane represents a possible solution. So for example, this point here, the point 3, 2, would represent I am producing 3 gallons of A and 2 gallons of B. But not all points in that plane are feasible. They're not all doable. Okay, so for example here, this point, 5, 5, 5 gallons of A and 5 gallons of B. How much X am I using? Well, 4A plus 6B, in this case, would be 50 pints of X, but I've only got 24 pints of X available. So that point is not doable. It's not feasible. So it would be useful if I could split up this plane into solutions that are feasible and solutions that are not feasible. Now, if we look at my constraints, 4A plus 6B is less than or equal to 24. That is a linear inequality, and the great thing about linear stuff is I know how to draw that. So I can draw that inequality. 4A plus 6B is less than or equal to 24. Okay. I know that all points above that line is not doable. Every point above that line would make something bigger than 24. And every point below that line would give me something less than 24. So I know I can only look at the points underneath that line. Similarly, for my Y constraint, I can draw that linear equality, and I need to be below that line. So all the points that are below both those lines are feasible. All the points that are above at least one of those lines, I'm calling not feasible. I can also not produce a negative amount of paint, so I can draw this region, which I'm calling my feasible region. Every point within that region is feasible, I can actually do. So one of the points in that region will maximize my profit. How do I find that? So like I did with the constraints, I can draw the line for my profit. Okay? But I don't know how much profit I'm making yet. Let's just pretend I'm going to make 0 profit. I will have the line 50A plus 60B is equal to 0. I can draw that. That's this dotted red line. Every point along that line will give me a profit of 0. There is only one point on that line which is feasible, which is the point 0, 0. So the only feasible way I can get 0 profit is by producing 0 gallons of A and 0 gallons of B. Okay. Now, I don't want 0 profit. I want more profit than that, so I can increase my profit. Increasing my profit would be equivalent to increasing my y-intercept. So I'm going to push that line up as far as possible while staying within my feasible region, and I can get to here. So whatever equation for that line is, every point along that line produces the same amount of profit. I know it's the highest amount of profit I can make because I pushed it up as far as I could. And there is one point that's on that line that's also in my feasible region, and that is the solution that optimizes my problem. That solution is 12/7 gallons of A and 20/7 gallons of B. Okay. So that's a brief introduction to linear programming. This was a fairly simple case. I had two unknowns, so I could draw things in 2 dimensions. I had only 4 constraints with my non-negative constraints, so it was a fairly constrained problem, fairly small problem. Using Python, it's very doable to reproduce this. Okay, so using Python, we can solve these linear program problems using a library called PuLP. And PuLP's a really cool library. It's mainly just a readable interface to these problems, and it will go off and use more sophisticated solvers underneath that does something more clever than what I just did, but the equivalent of what I just did. Okay, so in order to do what I just did there in PuLP, I will create a problem, and I'm saying that this is a maximization problem, because I'm trying to maximize my profit. I'll tell it what my unknowns are, my variables. So that's an array of 2 things. I can tell it what my objective function is, what is the thing I'm trying to maximize. In this case, it's my profit. Add that to the problem. I can add my linear inequalities to the problem. Then I can use the method solve and read off the solution. Okay, so this is just a nice readable interface to a lot of more sophisticated solvers. Linear programming was developed and refined around the Second World War. People were doing some stuff before that, but it really came to the form we've got it today around about the Second World War. And since then, there's been lots of variations and advancements. So for example, integer programming is a variation where we restrict our decision variables to just be whole numbers. This is really useful if we want to deal with stuff like people. We don't want to be sending quarter of a person somewhere. Okay. Multi-objective programming is when we've got more than one objective and we want to optimize them both, and possibly that means trading them off against each other. Stochastic programming is when some of our parameters are unknown, but we know roughly, or they can be variable, stochastic programming. And there's lots of other variations that I'm not going to talk about today. Okay. In this work, I used integer programming and multi-objective programming to solve this Pokémon problem. Okay. Integer programming in PuLP is really easy, and PuLP does this for us. We don't need to think. There's lots of sophisticated mathematical algorithms behind it, but we don't need to think about that with PuLP. We just, when we create our decision variable, we tell it this is, the category is integer. Similarly, I can say that this category is binary, and binary just means it's an integer that's either 0 or 1. That's really useful for yes or no questions. Multi-objective programming, though, we have to start thinking about changing our model. And a really simple way of doing that, when you just have 2 objective functions, is you just take a weighted average. Take a weighted average for all possible weights, and that'll give you all the possible best trade-offs. Okay. Right, back to Pokémon. Back to my problem of finding a team of 6. Okay, so if you're not familiar with Pokémon, there's loads and loads of data associated with Pokémon, which is what got me thinking about this in the first place. So meet Blastoise. He is one species of Pokémon. Okay. Blastoise is a water-type Pokémon. Pokémon can be 1 or 2 of 18 different types in the game. Okay? That type will determine what attacks he is weak to or strong against. Blastoise has 6 stats, so HP, attack, special defense, and speed. And these are just properties with numbers. The higher, the better. They will determine damage calculations and so on. The higher, the better. If the special attack is higher than the attack, we will categorize Blastoise as a special attacker, and vice versa, he will be a physical attacker. Okay, and that will come into play later on. As I said before, each species of moves can learn a subset of around about 68 different attacks, but each individual Pokemon will only have learned 4. These 4 attacks, Hydro Pump, Bite, Ice Beam, and Surf. Each move has power and accuracy that will determine how much expected damage there is. Each move has a type that will determine which Pokemon it is strong or weak against. And they're also either special or physical, and that determines which of the properties, the stats, is used in damage calculation. Okay? So there's lots and lots of stats associated with Pokemon. And I kept saying that there's these 18 different types, and it determines what Pokemon are weak or strong to different Pokemon. So if you've played Pokemon, you will have seen this table. This is a table of the 18 different types, and it'll tell you how much damage is being done. So for example, if you look at the third column the water column, a water attacking a normal type Pokemon will deal 1 multiplied the damage. A water attacking a fire type Pokemon will deal double the damage. A water type Pokemon attacking another water type Pokemon will deal half the damage. So we would call that being strong against or resistant to an attack or strong against a Pokemon. Okay. So the problem I went to solve then is I want to find the team of 6 Pokemon with the highest stats, each with 4 moves that maximize the expected damage. But I've got some constraints. I want that for each type available, I want a Pokemon in my team that can resist moves of that type. For each Pokemon my team, for each type, I want there to be at least 1 Pokemon on my team that knows a move strong against that type. But I also want them not to be weak against that type. There's no point to being strong against it if you're also weak against it. To balance out my team a bit, I want to make sure there are 2 special attackers and 2 physical attackers, at least. And I want my special attackers to only know special moves, my physical attackers to only know physical moves. That is my problem. I can now write a mathematical model of this. I can describe this mathematically. In order to do that, I need some decision variables, and I'll go through this fairly quick because I don't expect you to be able to read all this. Okay? But I have 2 sets of decision variables. XP is a binary variable that will be 1 if Pokemon P is in my team, 0 if they are not. Just a simple yes or no. And I have another set of decision variables, YPM. That will be set to 1 if Pokemon P knows move M, 0 if not. They are the things I am trying to determine. My objectives, my first objective is that I want to maximize the total stats. My second objective is that I want to maximize the total possible damage of all the attacks on my team. And for this, I am just multiplying the power and the accuracy together of each move. There's also another term here. Some of you who play Pokemon might be able to recognize what that is. If you use an attack which is the same type as yourself, you deal 50% more damage. So I'm just adjusting for that as well. And like I said, this is a multi-objective, so I'm going to find the weighted average of that. My constraints then, I need to make sure I'm only choosing 6 Pokemon, and each of those I'm only choosing 4 moves for. I want to make sure the Pokemon only learn moves that species is allowed to learn. I want to make sure there's at least 2 special attackers and at least 2 physical attackers. That my special attackers only know special moves, my physical attackers only know physical moves. And for each Pokemon, there's at least 1 type that resists moves of that type, and that there's a move that's strong against every type. So that's the full mathematical model. Okay, the reason I'm putting this up here for you is not to try and impress you with maths or whatever, but I do want to be able to say, that this is, this corresponds to about 622,000 decision variables and 623,000 constraints. This is a fairly big problem. There are ways I can reduce that down. There are little tricks that I can do, and if you're interested, I can talk to you about that later. And the equivalent PuLP code then, don't need to be able to read this, but I just want to point out a couple of things. It's all written in Python, therefore I can, all the properties, I can just query a pandas data frame and put that directly into my model. And for these collections of constraints, I can just loop through them. Sorry, go back to that. I want to solve this for every possible value of the weight of my two objective functions. When I do that, I get something that looks like this. This is another little space which is useful to look at, called the objective space, which plots the value of the first objective against the value of the second objective. Now I want to maximize both of these, so I want to be in that corner somewhere. But there's this line, there's this curve called the Pareto front, and all the points below that line are achievable. All the points above that line are not achievable because of my constraints. And I find that Pareto front, that line, by solving that linear program for every possible weight of the objective function. And I can start interpreting this. So for example, this point here represents a solution where my weight is equal to 1, and I'm only optimizing for the team with the highest stats. This point here is where the weight is 0, and I'm only optimizing for a team with the highest expected damage of their moves. And then all possible values in between represent different values of that weight. So I've got lots and lots and lots of optimal teams now. So how am I going to differentiate between those teams? How am I going to choose the best out of those teams? I'm going to battle them together. Except that'll probably take too long, so I'm just going to simulate a battle between them. Simulation is just sampling random numbers, comparing random numbers against each other, essentially. Okay? So I'm going to simulate the battles. How am I going to do that? I'm going to generate 1,000 random teams, and for each of my optimal teams, I'm going to battle them against all the 1,000 teams and just count how many times they won. When I do that, I get a graph like this. So my x-axis is that weight, which just represents different teams, and my y-axis is how many times they won, the proportion of teams. And I'm just going to choose the team which won the most times. And that team is this team: Venusaur, Blastoise, Scrafty, Braviary, Aggron, and Beware, with a particular set of 4 moves each. If you take a look, if I had a little bit more time, I'd ask you to take a quick look at that. This isn't a team you'd actually use in the games. Why? Well, look at Venusaur. Frenzy, Plant, Leaf Storm, Petal Dance, and Solar Beam are all grass-type moves. Why am I repeating moves that are all of the same type? You'd never use them. Okay? So I can refine my model, and I'm going to refine my model by adding an extra constraint, which will say that no Pokemon has more than 1 move of the same type. Rerun the whole analysis again, and I get a different team now. So now I get this team. And I really wanted to show you this, because what that shows to me is that this multi-objective linear program is really taking into consideration the interaction between the two objective functions. I added a constraint that only should have affected the moves of my Pokemon, but they ended up changing the actual members of my team. So that's showing that this methodology really is taking into consideration the interaction between those two objective functions. And very quickly, Pokemon was a lot of fun. I really enjoyed playing with a lot of Pokemon, but I'm an academic, I get paid for serious stuff. Why did I do this? Okay, but what I want to show you is that this problem and these solution methods are used all the time in managerial problems. Okay, so anything to do with scheduling, timetabling, staff rostering, coverages on networks, bin packing, transportation problems, so finding the greenest way around, pricing and urban planning. These are all essentially the same problem. I'm asking, should this nurse work today or not? Should this Pokemon be in my team or not? So all these problems are actually exactly the same problem as choosing a Pokemon team. So thank you very much. I've got a link to the GitHub here. I do want to mention this quickly though. This work was conducted in Welsh, so all my code is going to have Welsh docstrings, Welsh comments, Welsh variable names. I don't know if that was the right thing to do. So if anyone's got any comments on should I have done that, in order to make this reproducible, accessible work, I'd love to know. Thank you.